Today we shall discuss about capacitors. Capacitors or condensers. The popular name is condenser also. So capacitor is basically a device that stores electrical energy. So capacitor is capable of storing electrical energy in the form of electric charges. Capacitors have various of applications in electrical devices. Some devices such as a motor, electric pump or a fan require large current during startup. So capacitor provides the requisite amount of electrical energy that such devices require at startup. Some devices such as motor, fan, electric pump require high current at startup. Current at startup. So capacitor provides the requisite amount of electrical energy when such devices require high current at startup. For example, a fan might require current in the range from 2 ampere to 5 ampere. 5 ampere is too large, 1 ampere to 2 ampere. But this amount of energy that it requires at startup can be provided by some device which can store electrical energy, and this electrical energy is delivered at once, which is necessary for the working of these devices. Capacitors are also useful in TV or radio receivers where the capacitance of the capacitor can be varied as per requirement. Capacitors are also used in electrical devices like CRO or cathode oscilloscope, where it is necessary to produce a high electric field and a constant electric field that deviates the electron beam. CRT or cathode ray tube was also used as picture tube in certain TV or computer monitors. So in these situations, the capacitor also provides the large amount of electrical energy that those devices require. So the electrical energy is delivered at once. It stores electrical energy and the electrical energy is delivered at once. Energy is delivered at once. Now capacitors will store charge, and the charge that they will store depends on the potential difference. The charge, say Q, stored by the capacitor depends on the potential of the capacitor or the potential difference between its plates. Now, capacitors comprises of plates. Plates does not necessarily mean that they will be of rectangular or square shaped. Plates might be of cylindrical nature. Plates might be of spherical nature also. But the general terminology is that the capacitor has a set of plates and it can store electrical charge on those conducting plates. So the potential difference that exists between the plates is suppose V. Then the charge Q is proportional to the potential difference that will exist between its plates. And mathematically, there will be a constant C which will define the the ability of the capacitor to store some amount of charge, and this ability is called as the capacitance of the capacitor. So that C is called as the capacitance of the capacitor, and it does not depend upon either the charge or the potential difference. You see that C is obviously Q by V. The relationship might show you that capacitance depends on Q or capacitance depends on V, but it's not so. You can compare it with Ohm's law, where the resistance was equal to the potential difference by the current, but here the resistance does not depend upon the potential difference of the current. The resistance depends upon the length of the conductor, the temperature, and the area of cross section of the conductor. In a similar manner, you can say that capacitance does not depend upon the charge stored, it does not depend upon the potential difference between its plates, but the capacitance C depends upon capacitance C. It depends on the shape and size of the capacitor, or you can say it depends upon the dimensions of the capacitor, and it depends upon the medium between the plates of the capacitor. We will realize after some time that the capacitance depends upon the area of cross section of the plates, it depends upon the distance of separation of the plates, and that's why I have said shape and size, and it also depends upon the medium separating the plates. So now, when a capacitor is charged, it is connected to a battery. When it is connected to a battery, suppose this is a plate of a capacitor, this is another plate of a capacitor, it is connected to a battery. The battery will act as a driver of the electrons. It just pumps the electrons from one plate to another. So if this is the positive plate, then if this is the positive terminal of the battery and this is the negative terminal of the battery, then this plate, which is a conducting plate, will consist of large number of free electrons, and the free electrons will be automatically dragged towards the positive plate, and the negative plate will pump those electrons to the negative plate of the capacitor. So this will effectively develop some amount of negative charge, and this will develop some amount of positive charge. So a capacitor will consist of two plates, one is positively charged and one is negatively charged, and the same amount of charge is present on both the plates, but the nature is different. If this is plus Q, then definitely this is minus Q. Also you can say that if the charge density is plus sigma here, and the charge density will be minus sigma here, where charge density is equal to charge per unit area of the plates. The area of the plates are identical, but the separation between the plates is much smaller compared to the dimensions of the plate. If the separation between the plates is d, then d is much less as compared to the length of the plates or the area of cross section of the plates or the dimensions of the plate. So you can assume that the capacitor plates are of large dimensions or infinite dimensions with respect to the separation between the plates. You can say that this d is much greater than the area of the plates, d is much greater than the length of the plates. So the electric field that these plates will produce will behave like the electric field due to infinite sheet. That means this plate will provide the electric field which is, say for example, E plus, that is sigma by 2 epsilon 0, and this plate will also produce an electric field which is sigma by 2 epsilon 0. So in order to realize how the capacitance depends upon the dimensions of the plates, let us take the example of a spherical capacitor or isolated spherical capacitor, which just consists of a spherical shaped conductor on which some amount of charge is deposited. So let us take the example of isolated spherical conductor. spherical conductor. So suppose this is a spherical conductor on which some charge is deposited, say positive charge is deposited. You can also assume that negative charge is deposited and get the same result. The total positive charge deposited on the plates is Q. This is a conducting plate, so the charge will deposit on the outer surface of the plates or the sphere itself. The radius is capital R. We know that the potential on the surface of the conductor is 1 upon 4 pi epsilon 0 Q by R. So from this you can say that Q is equal to 4 pi epsilon 0 R times of V. But in the previous discussion we also showed that the charge on the capacitor is proportional to the potential difference and the constant of proportionality is obviously C. So from these two equations, if you compare them, you will see that the capacitance of this isolated spherical conductor is 4 pi epsilon 0 R. The capacitance is 4 pi epsilon 0 R. So you see that epsilon 0 is a factor which is called as the permittivity of vacuum. So if this particular spherical conductor was kept in a different medium, then this would have been substituted by the relative permittivity of that particular medium. So it depends upon the property of the medium. R is the radius of the spherical conductor. So it depends upon R, that is the dimensions of the particular spherical conductor. Now this type of spherical conductor or isolated spherical capacitor is not of much use because capacitance will define the ability to hold more and more amount of charge. So even if we try to increase the radius, it is very difficult to increase the capacitance much, because if we try to store an amount of charge that is equal to 1 coulomb, the radius will become very large. So that's why this capacitance is not of practical use. And then we switch over to some parallel plate capacitor or a spherical capacitor where there are solid sphere and a spherical shell that will togetherly comprise as the plates of the capacitor, or a cylindrical capacitor where a solid cylinder and a cylindrical shell will togetherly act as the plates of the capacitor. So let us take the example of parallel plate capacitor. Suppose we have a parallel plate capacitor having its plates which are of area A, and the separation between the plates is D. We assume that the plates are placed in vacuum so that the separation consists of vacuum only. So suppose this is the positive plate of the capacitor and this is the negative plate of the capacitor. The separation is obviously D. As we have already told that the dimensions of the capacitor are such that it is quite large as compared to the distance of separation between the plates. So these plates can behave like infinite sheets. So with respect to this positive plate, the electric field is in this direction. Suppose this plate is named as plate P and this plate is named as plate Q. And the electric field due to the positive plate is EP in this given direction, and the electric field due to this particular negative plate is also in the same direction. So it is EQ, and both have the same magnitude because both behave like infinite sheets for which field is sigma by 2 epsilon 0, where sigma is the charge density and it is equal. Now, sigma is definitely charge per unit area of the plates, where Q is the charge on the positive plate as well as the negative plate. Q represents charge on either plate, which is same. If this is plus Q, then this will be minus Q. Now we know that the positive plate will be at a higher potential, the negative plate will be a lower potential. So potential difference V will exist, and by the definition of potential difference as the negative of potential, by the definition of electric field as the negative of potential gradient, we know that V is equal to E into D. Which means that the potential difference between the plates is sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, because the net field E will exist in this direction from the positive to the negative plate, and E will be equal to EP plus EQ, as both are the same values. This is twice of sigma by 2 epsilon 0, that is sigma by epsilon 0. So this will give you sigma by epsilon 0 times of D. Now we know that Q equal to C into V, which means C equal to Q by V, that is Q divided by V, which is sigma by epsilon 0 times of D. This means C is equal to epsilon 0 Q by sigma into D. But you see that sigma is Q by A. Epsilon 0 Q divided by Q by A into D. And this Q cancels out, so this becomes epsilon 0 A by D. So therefore, we can say that the capacitance of a parallel plate capacitor is epsilon 0 A by D, which means that capacitance is independent of the charge on its plates or the potential difference on its plates, potential difference between its plates. It depends upon the area of cross section of the plates, it depends upon the separation between the plates, and depends upon the medium between the plates. If instead of vacuum, the plates are kept in a medium of relative permittivity epsilon r, then C can be written as epsilon A by D, where epsilon is the permittivity of that particular medium. We know that epsilon r is epsilon by epsilon 0, so this can be written as epsilon 0 epsilon r A by D. We could have achieved this particular result V equal to E into D in a different manner. Let me show that too also. So this is the positive plate and this is the negative plate. We name the plate as P and this is Q. And the charge on this plate is plus Q and the charge on this plate is minus Q. So electric field due to the positive plate was in this direction, electric field due to the negative plate was also in this same direction. We know that the positive plate is at a greater potential, so potential of P is greater than potential of Q, so that the potential difference V is definitely Vp minus Vq. By the definition of the line integral of electric field, we can write Vp minus dq is minus integration of E vector dot dl vector taken from the plate P to the plate Q. Now, the line integral has to be performed along a path connecting the positive plate and the negative plate. Because the field is uniform, and we know that EP and EQ are same, that is sigma by 2 epsilon 0. The net field is sigma by epsilon 0. So the path connecting might be a straight line path, and this is the direction in which E vector and dl vector will lie. So that E vector and dl vector are in the same direction and E is uniform. So this we can write it as V is equal to E times of dl, and integration along this path, integration of dl will produce the distance between the plates, that is d. So this is again E into d. So the same result can be obtained from the concept of the line integral also. So ultimately what we realize is that the capacitance is epsilon 0 A by d. It is independent of the charge deposited on it. It is independent of the potential difference between its plate. It just depends upon the dimensions of the plates and the medium in which the plates have been kept.